Now we're going to look at friction and heat in our energy calculations. So our setup here is simply a block on a ramp, and if I give it an initial velocity, I give it some kinetic energy with my hand, we'll see how high it goes. So in addition, our normal isolated system would just be kinetic got converted to potential, and then it should have slid back down. But it didn't because of friction. So friction is holding it up here, and it also acted as it slid up the ramp. So we've got to figure out how does that become involved. So we'll start with just our drawing of the system. Here is the ramp at an angle theta, and the mass starts down here, and we give it an initial velocity, and the mass ends up somewhere up here, and there it stops. And we're wondering is how high does it go in terms of this height? So we have a right triangle here, how high h, where the distance it actually traveled was d. So we're going to calculate this both in terms of energy, but also let's do it in terms of forces. And we'll see forces in kinematics, and we'll see if the two answers match. Now the forces in kinematics way is kind of long, and we've already done it in the past, similar problems, so I don't want to spend a lot of time on it. So what I'm going to do is go into YouTube mode. Hey everybody, thanks for tuning into my channel to do this calculation. Here we go. So we've got this thing and we have to draw a free body diagram. Okay, here's the mass right here, and we have mg down, and we have a normal force pointing up. Of course, we can break mg into a component along the direction down and perpendicular. Okay, so now we're ready to do it. So we're going to say sum of the forces parallel equals mass times the acceleration parallel. We're going to apply Newton's laws down the ramp. All right, so let's see. What are the forces parallel? One is the gravitational component down the ramp, mg sine theta. That's a component this way if that is also theta. Now, what about the other force? Also down the ramp, we have the friction force. Friction force plus the kinetic friction, mu k, times the normal force. What's the normal force? Well, it's the thing pushing into the ramp and pushing back, and it must be mg cosine theta. There's the sum of the forces equals ma, like that. All right, so now we want to say we're going to take this acceleration, and I can cancel the masses, a, and we're going to put that in v final squared equals v initial squared plus 2 ad. Of course, we know that the final squared is 0 because it came to rest. The initial squared is vi. So we have 0 equals vi squared plus 2, and the acceleration is this, but it's negative because it's accelerating down, and I find it up as positive, right? So it is minus g sine theta plus mu k. The minus is on the outside, so the minus is there, and the minus is there. G cosine theta. And then these two minuses could come out, make that a minus, these become pluses. Right, so we end up with vi squared equals all this. Vi squared equals 2 g sine theta plus 2 mu k g cosine theta. Oh my god, I forgot the d. Plus there's a d there, and therefore there is a d here. Oh, we got to deal with the d now. We went d, but we really care about h, so we just need to use the relationship that sine of theta equals h over d, right? So this d is equal to h over sine theta. H over sine theta, like that. Very nice. So now, if we bring all this together and solve for h, what do? Bring the sine theta up here, v squared sine theta in the top, sine theta in the top, and this whole mess down here in the bottom, 2g sine theta plus 2 mu k g cosine theta. Let's pull out the 2 like that. And let's pull out the g, why not? G sine theta plus mu k cosine theta. And there we have the height. Please like this video and subscribe to the channel. Oh my god. YouTube is so exhausting. Okay. Let's just calm down and let's do this with energy. That was the force way to do it. This was force. Let's do it with energy. So from what we've learned so far, you would just say delta k, delta k plus delta u equals 0, right? And you would do what we've been doing. Let's say we lost 1/2 mvi squared, right? We started at initial speed and went to 0, so that's minus 1/2 mvi squared. We gained some gravitational potential because we went up h plus mgh equals 0. So you solve for h, I think we were trying to find h, and you get h equals vi squared over 2g. Yeah, h equals vi squared over 2g. And that does not match this, right? That's because this is wrong. You can actually even tell that this has the mass going too high. Right? This is vi squared over 2g. this is vi squared over 2g with this extra part, and it's sine theta over sine theta plus something. And I guarantee you this something is positive because theta has to be between 0 and 90, so this isn't going to be negative. So the denominator is bigger than the numerator. Basically, it doesn't get as high. We know why it doesn't get as high. It's because friction took away some of the energy. So to do the energy part properly, we have to consider two things. One is that the friction force does work, if you want to think of it that way. And there's no reason it wouldn't. It's a force being applied to the block, and it's along the direction of the displacement of the block, so it's gonna do work. And another way to think of it is that heat, which is a form of energy, is generated. And since energy is conserved, that has to come from somewhere. So I know that if I slide the block up and down the ramp enough times, we know we'll generate some heat. So next board, we're going to think about these two and how to solve this properly with energy. Now let's analyze the situation and use the concept of internal energy. So where were we? We were going to think about the work done by the frictional force. Work by friction. So that would just be work. Well, it's just always F dot R, or F dot displacement. So in this case, we'll call it the force due to friction dotted with, we'll call it D. Because D is just this displacement vector as we go from the initial to the final position. And in YouTube mode, I went so wild, I forgot to label the friction force. There it is. This was the component of gravity that way, but there's also a friction force pulling it back. So if we want to put it on here, we can draw it like that. So let's see, we know the magnitude of the friction force is mu k, the kinetic friction, mg cosine theta. And we know the magnitude of the d vector is d, a little d. And the angle between them is 180 degrees. Right? So it's a dot product, magnitude, magnitude, angle between. Cosine of 180 degrees. So really that's just bringing in the -1. We know that the work is negative minus mu k mg d cosine theta is the work that we care about. So now to use this in a problem, there's sort of two ways to look at it. So one way, we'll call this view 1. View 1 is that the frictional force F frict, or what do I call it, FF, is an external force. So it's not part of the system. An external force applied by the ramp. So in this view, the system is just the block. All right. So you would just apply this idea, delta K plus delta U equals the external work. And we know in our particular problem, this is going to be negative. We just calculated it. In our particular problem, not in general. Right? So if that's negative, then the total energy goes down, and that is basically what we saw, right? So since this is negative, so energy is lost by the system, which is what we saw. We know when you do it with forces, it doesn't get as high if you include friction. So we didn't gain as much gravitational potential energy. So that's one way to look at it. Another way is that the ramp is part of the system. All right, the ramp is part of the system, and friction, work due to friction, creates internal energy as heat. Friction creates internal energy as heat. All right. So the way you could write this is you could also have a conservation or sort of an energy equation. You could say I'm going to conserve changes in kinetic energy plus changes in potential energy plus changes in, we'll call it EINT, internal energy. those must be 0. And this will be the case if the system includes the ramp and the mass, because all the heat you make will remain in that system. And you can see, how do you calculate the internal energy? Well, you just do this. It's just the work done by friction. So basically, this is negative. You just bring it over here. It's going to be positive. And then all these are positive, and you're just conserving a certain amount of energy. Some of the energy went from these two going down to this one going up in terms of changes. So neither one of those is right or wrong. You can think of it either way. Let's see if we can get it right here. So let's run the numbers and say, let's check using, let's use the top way. So the loss of kinetic, 1/2 mvi squared, plus the gain in potential is mgh, equals the external work, which we said is minus mu k mgd. Mg, actually, I want to put the cosine theta there and put the d there. All right, because we know that the d from the previous problem is h over sine theta. All right, so we'll put this here, h over sine theta. And all we got to do is solve this for h. So this term is negative, we'll bring it over here. Now we have two positive terms. This term is negative, we'll bring it over there. So all the terms are positive now, and we just want to pull an h out. H times, what's left here? Mg. Oh, every term has an m in it. Let's get rid of the m's. What's left here? G. And what about this term that we brought over? We pulled out an h, we pulled out a g, mu k, we pulled out an m, mu k g cosine theta over sine theta. Mu k g cosine theta over sine theta. Now I just realized, of course, we could have pulled out a g as well. I meant to do that. I apologize deeply for that. I forgot to in my notes as well. The other side came over here, and we canceled the m, so that's vi squared over 2. All right, and we can simplify further. We're going to pull a g out of here, and then put the rest underneath, and we're going to get that h equals vi squared over 2g, and that is all going to be times what? We're going to put a sine theta up here and multiply the bottom times the sine theta, and we pulled out the g. So that's all going to be sine theta plus mu k, and then it'll cancel that sine theta, cosine theta. And I sort of worked it into that form because that matches what we had calculating it by forces. So, of course, as we should, we get the same answer whether we do it with energy or we do it with force. So, in whatever physics class you may be taking or whatever book you may be reading, you'll find this is sort of handled sometimes in weird different ways, this idea of heat and internal energy. One way to think of it is heat is the random thermal motion at the sort of atomic and molecular scale. So you could say it's still kind of like kinetic energy. So sometimes people distinguish between coherent motion, the mass, all its atoms and molecules moving together forward, and incoherent motion. We generate heat and it's still the atoms moving, they're just not moving together, incoherent motion. So we're really just converting some of our kinetic to incoherent kinetic is one way to think of it. But you can also do little mechanisms for how friction works. When two things rub against each other, you get a little pull between little asperities stick together and they pull on each other. And in that way, you can imagine little pieces of the ramp are moving, and you can think of the work done on the ramp. But really, the way we described it, the ramp never moves, so we have no work done on the ramp. So all these different models and ways to think about friction all end up working like basically one of these two. So I just went with those two basic ways to describe it. Some forces can be classified as conservative. So what we're going to talk about here is very important at a fundamental level. In terms of your day-to-day life and doing physics, let's cover it anyway, because it's so fundamental. We have to cover conservative forces. My plain-spoken definition of conservative forces is they don't waste energy. All right? Now let's go to the textbook definition of a conservative force. A force is conservative if one of two things. Here we go. One, work done by the force, work done by the force on a mass is 0 through a loop. I should say the total work. So let's think about the gravitational force, and let's think about this piece of chalk here. So here is an XY coordinate plane. And I'm going to take this chalk and I'm going to move it through a loop in this plane, right? So here is the loop. It doesn't have to be round. I'm going to move it around like this. I'm going to start here and move around this loop. And let's think about the work done by gravity, the gravitational force. First, I'm pushing up. Oh, I'm having to do a lot of work. All right, so negative work from gravity. Oh, and then now I'm coming back down. Oh, gravity's helping me out. Now positive work from gravity. Oh, thank goodness. And now, oh, I'm going back up again, negative work from gravity. If you added all that up, it'd be 0. The work done by the gravitational force through the loop is 0. So gravity would probably work out. A second definition is work done by the force from A to B is independent of path. So you don't have to just do this for loops. You can say, I'm going to go from here to here, B. So you can tell you're going to have to push against gravity, right? You're going to get some negative work from gravity. But if you go here to here just in a straight line, oh, okay, I had to do so much work, negative work from gravity from there to there. But what if I went all the way up here and back down? Oh my God, even more negative work from gravity, but now some positive work from gravity to make up for it. In the end, it's the same amount. What if I go down first? Oh, positive work from gravity. Now we're liking it, but now I gotta push back up, negative work from gravity. In the end, it balances out and you get the same thing. So it doesn't matter which way you go. You have the same amount of work from the gravitational force as you go from A to B. So gravity is conservative. So let's see, so of conservative forces, we know 2 so far in this class. 1 is gravitational. Force is conservative. It follows these rules. The second one is the spring force we calculated. If you went through and did all this math, you could do it in one dimension for a spring. You'd find both of these are true. A loop would be going from one place back in and back. It'd be the same. A to B would just be you go A to B like this. Here's a spring. You could go from A to B, or you could go from A to B by going A out to C back to B. However you deal with a spring, it'll always be conservative. A third one that you may have heard of from other courses would be the electrostatic force. So if you take 102x, we'll talk about that force quite a bit, and it is conservative. Examples of non-conservative forces are ones that do waste energy, and of course the one we can think about is friction. So here, let's do some non-conservative force, and of course there is friction. So I'm going to break my chalk now and say, let's think now, instead of about the gravitational work, let's think about the friction force as I go around a loop. We'll start here, and the friction force is pushing back. The system's losing energy. I'm having to push. I'm losing. I never gained, right? So this net work was not 0 going around the loop. I always lost. And if I look at what I lose going from A to B, lost the whole way. But what if I go up here? Oh my God, I lost a lot more, right? You never change direction and gain with friction. You always lose. So friction fails on both counts. It is not a conservative force. The other one, similar to friction, is drag. We did our air drag and our liquid drag, also not conservative. So you want to be able to identify the differences between those two. It's a very fundamental difference.